Right. So, is that readable? Which I mean, I can go into full screen, but
It's, it's
can
good for
can can
me.
anybody read that font?
Yeah.
Yeah, read that one.
Okay. So this is a bit of an update. I think I can't remember whether I spoke last time this and a good number of months ago. Anyway, so I've done a couple of things. One is talk about what I've played with the hardware because, of course, you can't leave hardware alone. So originally I was running a Pi Zero on this, and all the instructions on the GitHub page are for the Pi Zero. I've swapped to a W, the wireless version of this, and you can see. I've got some more photos, but you can see on the. I've actually put a bit of strip board on the connector, on the Pi Zero connector, and run power to that. I also have added a buzzer now. One of the advantages, I was running the Pi Zero off the four-way connector, the serial connector, including the power. It was okay, but I had occasional. I didn't have any power outages, but I had occasional serial problems. This appears to be a bit more stable. I also put a 3-volt 3-buck regulator underneath. It's lost me a couple of millimeters of clearance. Currently, I haven't got the bottom board lowered as much as I could do, but I have got a few millimeters. I could take it down. So that's sort of what I've done on the hardware. That seems to run okay. What I wanted to do was talk a bit about. Let me talk about the Nano. So I don't know whether the last time me and Pete had worked on sort of UKMARS, which is the Nano software, the command software. And after that, I think Pete came to controller. The original controller wasn't as good as he liked. So he swapped to this sort of incremental control that he spoke about last time. And I've ported that onto the UKMARS now. So that's the same controller, speed rotation controller that is running on UKMARS, the Urinal UK, the Maze Runner. So all that's been ported across. I've also, I've decided to put or try the steering adjustment, which is sort of keeping it in the middle of the cell based on the left and right sensors on the Pi. As you'll all remember from Pete's code, he obviously does that in the Nano along with maze solving. I'm sort of interested whether I'll have enough, whether it'll be good enough. I think it will based on some basic tests, but the jury's out. It's relatively easy to swap it back to the Nano if we want. I was running 115k. So as far as now, barring me finding bugs, the sort of Nano command software is working. Operates in a couple of modes. You can put it into sort of verbose and an echo mode if you're running it from a terminal window. The Pi software turns off the echo in order to save a few bytes of bandwidth. It's actually got two modes. It can actually listen for the OKs to validate all commands, or these three sorts of verbose modes, and it can knock those down. It's got some options in the Pi Zero software. I thought I'd mention what I've been doing on the debugger. So originally, when me and Pete were working on UKMARS, the Nano software, although I was running it from the Pi Zero occasionally, most of the time I was running it from a PC or a Mac over either a USB or a Bluetooth module. I'm running the Python software straight off the Mac, running it as a sort of remote control robot. Over the last few weeks, I've actually been running it from the Pi. Now, because I swapped over to a Pi Zero, I had a couple of options. Pi Zero W. I had a couple of options. One was to run over the Wi-Fi, which is what I do on one of the other robots I've got. The other one is theoretically you can also set the Bluetooth up as either a client or a host. I started on that, but I never got round to finishing it. So currently it's running all over on Wi-Fi. And I'll talk about that, what I actually do when I'm developing in a second. When it's standing still, it's still running off a nickel metal hydride battery, 9-volt battery, for both the Pi Zero W and the Nano and the motors. Obviously, if you're doing some standing still debugging for a few hours, then it gets through nickel metal hydride batteries. So I've got a 4-amp PSU I used with one of the other robots when I was doing sort of stationary testing. Connected a PP3 connector to that. Put SSH keys on the Pi Zero so you could just log in. Added an extra library, the GPIO 0 for the buzzer. Oh, I added a buzzer onto the hardware just because I could. Not mandatory, just a bit of it. It's a self-oscillating buzzer, so just a bit of beeping when I want to hear it when it's moving. I've got I can probably actually show you this, but I've got 2 terminal windows open most of the time. I use an rsync command that I put in this presentation notes just to sync it. So that previous I'm on Vision 2, I actually had a Git client on the Pi Zero. I'm not doing that here. I just run rsync and it synchronizes it from my laptop. And then generally I've got an SSH connection running all the time. And then I'll for instance, to give you an example, I might run, for instance, the buzzer test. And there's a few test programs. Most of the ones at the moment I'm running. My original plan for this was to data sensor test, which does the IR sensors. Then I had one to do a circle pattern. It runs straightforward, does a circle, runs and finishes that runner. My current I sort of swapped off to sort of port the high level stuff over to a Python file. So that's the maze solver that I'm sort of in the progress of at the moment. So this is up. So yeah, SSH into robots, pull Python 3. When I actually run this on the robot for real, I'll get it launched the Python script from RC local. I'll probably actually run it under screen. So screen and tmux for anybody that hasn't used Linux or Unix, a sort of a virtual terminal. Now, the advantages are that it captures the standard out, which means that you can effectively, even if you disconnect from your terminal session, you can connect to that screen session and see what it's been printing out. On previous robots, I've written to a log file, which you can do, but it's a bit more work. Also, I've been running Minicom. Obviously, I can plug a USB cable or straight into the Nano and sort of fiddle directly with the command language. But you can also just run Minicom, a serial terminal on the. So this terminal window, which you probably can't see, it's the font's too small. I'll zoom it up a bit. You can run Minicom on here. And this is actually that's the Nano talking to the Pi. If you want to do various like sensor tests or whatever to find out what the sensor's doing. I guess maybe before I go on to the next slide, I don't know whether I covered a bunch of stuff about debugging. Obviously, you'll get copies of these slides. If anybody's doing anything on the Pi, I guess people are doing sort of similar things, but I thought I'd cover what how I was sort of debugging it. Obviously, if it's doing complicated movement, then you're sort of stuck to printf and the like. and maybe log files on the Python. I have got a mode where it will log all the commands it will send down to the Arduino, and it doesn't save that while it's running. It saves that at the end of the run. Before I go on to the sort of Python software, has anybody got any questions about the debugging on the Pi?
Okay. So are you running? You said you were running some of it, or at one point, just as a remote thing directly from the Mac. Is that the Mac running? So that's the Mac running the Python software.
Yeah, I mean, you can just
directly.
Yeah, exactly. So I mean, I'm gonna lead here, but you could effectively go into. If I just go into the.
Perhaps it would be worth reminding folk that the actual connection to the Nano is via its serial port, which could be a Bluetooth or physical connection. And so, because all of the commands are just text sent over the serial port, it doesn't really matter how you get there. So you could be sitting on a PC somewhere, connecting via Bluetooth and a serial adapter and talk to the Nano and tell it what to do. Or you could have the Pi Zero or anything else for that matter poked on top of the robot and connected via the serial port, and the effect is the same.
Exactly. It's quite interesting actually, because I was prior to this, I was basically running all of these Python scripts on the Mac, and I've actually got some abstraction in the code. It's probably going to be a bit small, maybe, but if I go into Python, there is a robot libs and some general. He says, looking manically for the file is. So these there's a set of commands that you can run that are so you can just call a Python function to read a GPIO input. You don't actually need to remember what the commands are. But there's also a there's also a file that that abstracts the interface. So which obviously I can't remember. Oh, here it is. Right. So this robot settings, one of the things it does is, so I don't even need to effectively switch the serial ports, because when it boots, it detects whether it's running on a Raspberry Pi or on a Mac or on Windows. Now, obviously, you might need to switch the serial port depending on what it's running on. So if I plug like one of those HC05 dongles into the Arduino, into the header on the UKMARSBOT, you can just run this and it'll do the right thing as long as this serial definition's correct. Then it'll run the host program, if you like, from the Mac, or you can run it from this is on the Raspberry Pi, or you can run it from here. You can use it as a remote control robot, which is sort of interesting. I know, Pete, I think you're interested in that as well.
Of course, this
go. A very simple remote control that just sends some, individual characters move left, right, forward. That could be a two-part thing, or it could just be a wire connection, or there's lots of possibilities. Once you separated out the UKMARSBot and what it physically does and who tells it what to do, how you link them together, there's lots and lots of possibilities.
Yeah, and this of course brings up a question about whether we should allow a remotely controlled mouse, from something else. It would also mean that you could put a Pi at the side of the maze, and you wouldn't have to power it on the thing. You wouldn't have all the problems of powering the Pi. It could just remotely run it, which I think would be a perfectly good thing to do.
I think it would be very entertaining if somebody could take. So, I mean, if we had like a camera feed for the contest, right, and if somebody could tap into that and use that to control the robot, I'd be well impressed. Be like the Robo Soccer.
It does. You could put a camera at the top,
yeah,
and control it, and that would be impressive.
I was also thinking just now when you were talking about the moving the steering control onto the Pi. What if the Pi Zero will run a Pi camera, will it not?
Yeah.
Yeah. So suppose the Pi Zero did some image processing, and at the moment in the Maze Runner code, the sensors calculate the cross-track error, right? The deviation from center line. So suppose the Pi could use the camera either for line following or for in the maze, and generate the cross-track error and then send that to the MarsBot.
Yeah. So I mean, I had it wasn't a UKMARSBot, but I had Duncan probably remembers it, rather shortened. I got a PyGo Pi, which is quite a big robot with a Raspberry Pi on, and that was detecting the line position for line following. I'd also got code that run on my original Vision robot that actually runs on the Pi that looks at the maze, and in fact so I have actually got code that potentially that I could port across to the UKMARSBot maybe to do some of that, given enough time and enough hours in the day.
The problem is it's always going to be slow if you use a camera, because you only got 50 hertz frame rates or something.
Yeah.
So you're only going to find out where you are every 20 milliseconds, even if all your video processing is incredibly quick, which it probably won't be.
This is very true, but you can also see further ahead.
Yeah, you don't need that sort of rate of processing. If you can see further ahead, because you can make predictions between the where it is and where it thinks it's going to be. So it only needs to be able to work out that it's not pointing in the right direction quickly enough to avoid the wall.
Yeah,
and you can also generate on the camera, the optical visual processing camera, whatever you want to call it, on that box, you can generate a trajectory that is followed virtually. So you're not really doing this kind of frame by frame or instant by instant control. You're creating a virtual trajectory for the robot to follow.
Yeah, I mean, in my opinion, the problem isn't, and obviously on the you can always leave the IR sensors on to do some processing as well. But the problem, from my point of view, for anybody doing camera stuff, is the giant mountain you need to climb up to do the simple stuff at the top. Right. So I mean, maybe if we get a bit further on to having like a Pi on a maze solver, then we've got some people working on maybe some basic libraries, and maybe it makes it much more accessible. I don't think in my, although I mean there's a lot of pixels to process on any image, but you can actually do quite a lot very simple stuff. But it's the fact that you've got to assemble the whole thing and then get all the software working, which makes anybody who's doing line following or maze solving with a camera, it increases the amount of effort they've got to spend. I wouldn't like to think, but maybe doubles the amount of effort they've got to spend, perhaps.
It is all running before you can walk. I agree.
But in principle, I think that maybe it does help. Anyway, we'll see. One thing at a time. So my plan. Let's talk about what I've got. So I think I've talked about this. I've shown you some of the libraries and stuff. I've got a sort of commands file that all those sort of command strings that you can see on here on this UKMARS front page on GitHub. So you don't on the Python software, you don't need to issue all of these commands. You can just sort of ask it for a set of sensor readings So that commands file abstracts that away. And sort of now the thing I'm doing is sort of porting or re-implementing in Python the sort of maze solver from Maze Runner. Currently, I'm actually playing about with some sort of background monitor task. So, you know, you want to be able to tell it, you want it to take care of sort of the low-level control and the steering while you're waiting for it to do sort of a mid-level control thing. That's what I was playing about with over the last sort of week. Yeah, and those are the links. So I think, I mean, what we really want is for it to do what we did with Maze Runner, which is, you know, have a sort of skeletal maze solver with on the Pi, which is not quite there yet. But I don't think it's, well, yeah. All the low level stuff's done, and go ahead, Pete.
We say quite often when people ask us at competitions about building the robots and doing this, that, and the other, one of the constant things is about the difficulty of solving the maze, and almost universally our response is it's the last thing you want to worry about because it's almost the easiest. And that'll be the case here as well. Once there is reliable communication, good feedback from the robot, and adequate control, making it do what you want to do at a high level is a relatively straightforward thing, I would hope. When we were, I haven't looked at it for a little while, I confess, I've been playing with other things, but when we were both looking at the UKMARS software, one of the things which I don't think, and I don't know if Rob agrees, but I don't think we really kind of bottomed out is exactly where the boundary should be between what the Nano on the MarsBot is responsible for, definitely, and what the Pi host is responsible for. Clearly, you know, generating the motor speeds and things like that, and actually reading the sensors is not something the host can do. The Nano has to do that. But somewhere in between there and the high-level control of move forward 20 centimeters, turn right, or perform an arc at 16 degrees per second, or whatever it might be, somewhere between those is a boundary which I don't think we've really, you know, kind of clearly defined. So if anybody has the time to have a look at this and have a think about it, I'm sure we would be appreciative of any suggestions as to, you know, where things are placed. And
agreed. Even just reading through the command list, so it sort of grew organically, and there's some very low level commands about, you know, reading and writing I/O, which was useful when I just soldered a buzzer on. But there's also that sort of high level sort of different sensor reading, and there's a question about, you know, what I suspect different people are going to tackle this differently. That's going to be my impression. That different people are going to have different opinions, and how much it's not just what level of control you put on, you know, in terms of high level or low level control, but it's also just a general approach. It's easy once you're starting to go down your own path to think that that's the only approach.
Mm-hmm. And presumably a lot of it is dictated by the link speed. So as you say, you can't send 1,000 commands a second to it to do something like check the sensors and do things. So anything that's got to be done repetitively at sort of millisecond type levels is going to have to be done on the Nano, while the other one's going to be doing, you know, all the high level solve, you know, get the sensors once a cell and solve the maze and that sort of stuff.
Yeah. I mean, I haven't measured on a real, you know, apart from doing, we measured some of the timing for commands. So, for instance, we print some of the stuff we print, like the battery voltage. You can get it to print it as a decimal, like, you know, 8.9 volts, 8.9 as a floating point, and there is some time taken to do that conversion. But I think what we were seeing is that even those conversions were being, we were sort of almost beating it was sub a millisecond to output that command. So, I mean, there is a question about, me and Pete had a brief conversation about whether these commands should be as terse. So most of them are sort of single, double letter, or full characters. At 115K, you're talking about, if you're turning off the echo, then I guess you got 10 kilobytes per second in both directions, theoretically. The Arduino won't keep up with I think it's going to top out somewhere between 1,000 and 2,000 commands, maybe. Whether you actually get that rate in a real connection is a different matter.
Especially a wireless connection.
Yeah, I mean, that introduces a whole different ball game if you're talking about Bluetooth or BLE, right? But even on a serial connection, our conversation was, it was unlikely we were going to be able to do. I mean, on a different play, if you had a higher speed link, you might have even decided to do the speed and the rotational control on the host, as opposed to on the sort of on the Nano.
It would wreck your control loop, unfortunately. But the delays would wreak havoc with your control loop.
You need something predictable, don't you, for the delays,
real time. But also,
so I mean,
I think even at 115 kilobaud, you can process, you can send without too much grief, maybe 100 commands a second. If you up to 20 or 30 bytes in a line, you can actually get a surprising throughput.
Yeah.
Mm-hmm. But is that the same while the thing's going along at 3 meters per second with all the interrupts coming in for the wheel counters?
Yes, I think so.
Yeah.
The maximum load that I recorded, I think, was about. It's got a 500 hertz control cycle on it, in the Maze Runner software, and obviously the amount of load taken up by the encoders depends on how fast you're going and what the resolution is. But I think I got it about 40% or thereabouts. Yeah. So there's surprising amount of steam left in it, I think.
Yeah, for a poor Mega 328, I'm actually surprised. Compared with, I mean, if you swap it for almost any other micro nowadays, you gain almost 100 magnitude processing power.
Yeah, but optimization. I've done nothing. There's floating point where I wanted floating point and stuff like
lots
that.
Of floating points. Lots of floating points. Yeah. So yeah, I mean, I think what I will do, Derek, at some point when it's running properly, as opposed to just sending a couple of commands to do some basic stuff. But when it's running properly, what I'll do is I'll actually put some. Well, I'll run a capture with timestamps, and we'll get an idea of how many actual commands it's running on when it's actually doing real maze solving, for instance. I think that'd be much more. We'll get a much better idea of the realistic sort of throughput of commands. Because I certainly can run 1,000 commands a second on it, but it's not very realistic depending on what the command is. I mean, a lot of the time we're going to be waiting for either sensors to change or I suspect there'll be a bunch of polling, and there is actually mechanisms so you don't need to poll. It can return unsolicited messages, but I suspect at the moment it's going to be polling for either when the controller's finished or when the sensors are changed state. And we'll probably read the sensors during the idle loop, sort of back to back when we're not doing anything.
I think if you could get a high level control kind of loop rate of 50 to 100 frames a second, I think that would be quite respectable for what it is.
Yeah. Okay. Any other questions?